The first specification error that we are going to discuss is that of underfitting a model. Underfitting a model basically means when you're omitting a relevant variable. For this discussion, we are taking this example where the first equation represents the true model or the correct model. So you have yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus the error term. So we have two explanatory variables x2 and x3. Instead of running this true model, suppose we commit a specification error and we run regress yi on only x2i. So the second equation, where we have alpha 1 and alpha 2 as the parameters, represents the misspecified model. Now, as you can see here, the error term of this misspecified model will actually be capturing the combined influence of error term ui as well as beta 3 times x3i. What I mean is, if you compare these two equations or these two models, both of these terms together will form the error term of the misspecified model vi. Now, the consequence of omitting a relevant variable would depend on a few things. If x2 and the omitted variable x3 are correlated with each other, in that case, remember that the correlation coefficient between x2 and x3, which is r23, will be something different from 0. And if there is a correlation of this sort, that would mean that your intercept term alpha 1 as well as the coefficient of x2 alpha 2 will be biased, and this bias will not be something that goes away if your sample size is large enough. So they are biased as well as inconsistent. Inconsistent is a statistical term that we use when the bias does not go away even if the size of the sample is increased. The second consequence, that is, if your x2 and x3, the omitted variable, are not correlated, in that case only the intercept term alpha 1 is biased, whereas alpha 2, the coefficient of x2, will now be unbiased. Another consequence of omitting a relevant variable is that sigma square of the population, that is the variance of the error term, the original error term ui of the population, will be incorrectly estimated. If sigma square is incorrectly estimated, the variance of the OLS estimator in the misspecified model, that is alpha 2, will be a biased estimator of the variance of true beta 2. Okay, and because of this, your usual confidence interval and hypothesis testing procedures will give you misleading conclusions, especially about the statistical significance of these estimated parameters. And in addition to this, any forecasts or predictions that you make based on this incorrect model will also be unreliable. Now let's look at the technical portion of the consequences. Basically, this is the technical explanation for the consequences. Now, if you run the misspecified model, remember your original model was yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui, right? And you have not run this model, you have run the second model, which is alpha 1 plus alpha 2 x2i. That is, you are omitting this model. So since the model is different, the error terms have to be written using a different letter, that is VI. And like I said, the combined influence of beta 3 x3i plus ui is what is coming under VI. Now, when you take the expectation of alpha 2, as you can see here, when you take the expectation of the alpha 2 hat, your value comes up to beta 2 plus beta 3 times B32. Here B32 is basically the slope of regression of x3 on x2, right? Your B32 will be 0 if x2 and x3 are uncorrelated and independent of each other. In that case, like I said, your alpha 2 estimator, alpha 2 hat, will be an unbiased estimator, right? But generally, these omitted variables do tend to have some sort of correlation amongst them. And here notice that even if the sample size does become large, as long as x2 and x3 are related to each other or correlated to each other, this value will be something other than 0, and therefore the bias does not go away even if you have a larger sample. Now, the variance of the misspecified model, alpha 2 is the coefficient of x2, can be given as sigma square divided by summation x2i whole square. On the other hand, the variance of beta 2 hat, which is the coefficient of x2 in our true model, will be given by this formula. We came across this formula even in the case of multicollinearity, right? So we have sigma square by summation x2i whole square times the variance inflationary factor, 1 by 1 minus r23 whole square, that is 1 minus this term, 1 by this term, is called the variance inflationary factor. So what does this mean? It means that alpha 2 hat is biased, no doubt, but the variance of alpha 2 hat is actually lesser than the true model, true parameter estimate. As you can see, this value is less than the variance of the true model beta 2 hat. So when you're omitting a relevant variable, you have a trade-off between unbiasedness and getting an estimate which has a smaller variance.
And now there's an additional point that I want to discuss, which is that the sigma square that you have estimated, that is the variance of the population term that has been estimated from the misspecified model, will be different from the sigma square when estimated for the true model. This is because if you remember, sigma square is a function of, or at least sigma hat. The sample estimate of sigma square is sigma hat square, which is the RSS divided by the degrees of freedom. So sigma hat square is the unbiased estimate of sigma square, population sigma square, and it is given as summation ui hat square divided by the degrees of freedom. And in the case of the misspecified model, if you remember, we had estimated only two parameters, alpha 1 and alpha 2, whereas This is in the misspecified model. Okay, whereas in the true model, remember we have a true model, our sigma hat square would be summation ui square divided by n minus 3, because you're estimating three parameters, beta 1, beta 2 and beta 3, and hence you lose 3 degrees of freedom. So here it's vi by n minus 2, vi square hat square, and here it's ui hat square by n minus 3. This is why we say that the sigma square of the misspecified model and that of the true model will be different, because the residual sum of squares as well as the degrees of freedom will be different. So it is quite possible, and this is the point that you should remember, that if a regressor or an explanatory variable has a very strong influence on the y variable, then it may reduce your residual sum of squares. If you remember, residual sum of squares is basically that part of variance in y variable which is not being explained by the variance of the x variables. So it is the unexplained part of the variance. So if a particular regressor has a very strong influence on the regressant means the y variable, it is possible that it will have a large or important contribution towards reducing the residual sum of squares. And this benefit of reducing the residual sum of squares will far outweigh or will be greater than the loss in the degrees of freedom. Remember, if you add one more explanatory variable to the model, you are losing one more degree of freedom, because when you add x3 to the model, you have to estimate another coefficient beta 3, and that means you're losing one more degree of freedom. But like I said, if the x variable x3 that you are introducing into the model has a strong explanatory and influencing power on the y variable, then the gains that we get from reducing the RSS will be more than the pain of losing 1 degree of freedom. And additional advantage, when you are including x2, x3 into the model, it also reduces the bias in the estimators. And because of this, it will increase the precision of the estimators. However, if the relevant variable has only a small impact on the y variable, that is, we are talking about the variable x3 now. Suppose x3 has only a marginal, that is a very small, not very huge determining influence on y variable, and at the same time, if x3 is quite highly correlated to x2, then including x3 into our regression model may reduce the bias, which is good, but because the correlation factor is high, multicollinearity is high, your variance inflationary factor will be much larger. And because of this, if you remember from multicollinearity, since the variance inflationary factor is larger, the standard errors of the estimates or the coefficients will be much higher, and this makes them less efficient since the variance is higher. So here once again we are seeing why there is a trade-off between removing the bias or increasing the precision of the OLS estimators. So which to choose? Do you want to give your priority to reducing the biasedness of the estimator, or do you want to give your priority to reducing the standard errors of the coefficients? Will depend on the relative importance of the various regressors that you are considering. So econometricians all over, they suggest one thing, that always use a model which is formulated based on relevant economic theory rather than just shopping around for models or just trying and fitting any model that comes to your mind. Base your model on relevant theory rather than any other factor.